So let's have a look at a really important part of signals and systems. This is called convolution. Now, if we write it out here, we could say that if we had a function f of t and another function h of t, we can convolve the two together. So the sign for convolution is this little star. And in the end, when we've convolved these two together, we get a third function, g of t. Now I'm going to show you this in a two-dimensional sense here. It might not make a lot of sense when I show you it in this two-dimensional, but on the next slide I'll show you it in 3 dimensions, and I think it'll make a lot more sense to you. You'll have possibly have a real aha moment. So the idea behind convolution, well, let's imagine just any sort of random system. By a random system, let's say we're doing something really ridiculous. Let's say we're dropping pebbles into the sand. So you've got a flat bit of sand and you're dropping a pebble into it. You know it's going to make a little circular indentation, but you know that there's going to be scattering of the sand, so it's not going to be a perfect shape of the pebble. It's going to be some sort of strange sort of shape it makes in the sand. Now you could take that bit of pebble and you could shift it and drop it into another bit of sand, and you get the same shape, and another bit and you get the same shape. So there's nothing really interesting there. But the interesting thing happens is whenever you drop the pebble into a bit of sand and then you only move at a short distance, so that the next time you drop it in, the hole from the second drop impinges on the hole from the first drop. So it means that whenever you've dropped it in the second time, that second drop affects the first drop, and so on and so forth. So in effect what's happening whenever you're dropping them in like this and you're generating some sort of hole or some sort of surface, it's generated via convolution. That process of dropping pebbles in the sand and creating some sort of a shape where one pebble dropping impinges on the other, that is in effect convolution. Now another thing about convolution is that, and most important thing that we're interested in here, is that convolution in the time domain is equivalent to multiplication in the frequency domain, and equivalent multiplication, the convolution in the frequency domain is equivalent to multiplication in the time domain. Now we're going to go over that over the next couple of videos, so we'll see that later on. I'm just trying to give you some motivations for why we convolve things. Now another example here, and we'll talk through in this 2D approach, is that if we imagine f of t defines some sort of system, so that's the response, that's the description of a system in a purely functional sense. So let's say we put a signal into this system, so this signal is h of t. Then the first thing to note is that whenever we put this signal into the system, the first part of the signal isn't this part here, because this is 1 second later. The very first part of the signal is at time t equals 0, which is this part here. So when we start off the idea here of convolution of a function with some sort of system, what we're going to have to do is we have to take one of these. So in this case here, to make it simple, we'll take the h of t, which is we could define as a signal, and we'll mirror it in the y-axis. So instead of having a height 2 along 1, it's going to height 2 and along -1. So have you seen that drawn here in this drawing? Okay, so that's the triangle in effect being flipped over on the y-axis, and we do that because we want the very first signal to get in to be the signal at t equals 0. So now we've got some function here which is going to be, instead of h of t, it's going to be h of minus t. Now we don't call it h of minus t. When we're going through this process here, we're going to use a dummy variable, and it'll become apparent whenever I show it in 3 dimensions what the dummy variable is and how it works. So instead of being h of t, we'll call it our h of tau, and of course it's been flipped in the y-axis, so it's actually h of minus tau. So this little triangle here is h of minus tau. Now what we want to do is we want to shift it along in time, so we're going to add a time component to it. So we're going to add this little component here, which is a component of t. So you're going to have h of minus tau plus t, which would be, say, one of these, and let's say it was adding on t1, t2 and t3, so there would be t1, that would say be t2, and that would be t3. So rather than writing h of minus tau plus t, it's the same as h of t minus tau. So we actually write it as h of t minus tau here. So in this drawn here, you've got your h of t minus tau, and this one here, again, we've used the dummy variable for time called tau, so we're left with our f of tau. So it's exactly the same, other than the fact we've used this dummy variable tau. So the process of convolution is the process of sliding this function over the top of this function here. So I've got this function f of tau drawn, and as we slide that over, the height of this function is just 1. So whatever happens whenever we slide that across, all we're doing is multiplying it by 1. So when we've multiplied these two together, all we're going to get is this new function here. Well, that would be h of t minus tau times f of tau. And you can see that if this were to move all the way in, so the triangle sits all the way inside this little box, then the full triangle area would be defined, and as it moves further out, only part of the triangular area will be defined. Now what we would then do is we integrate all of these up from minus infinity to infinity, and in effect by integrating we take the individual, the area at each point in time, and the area becomes the height of this new function g of t. So we get this kind of effect here at the output. So the convolution then is the integral from minus infinity to infinity of h of t minus tau f of tau by d tau, and this is the output we get when we convolve these two functions. Now it's a bit of a mouthful that, and I've been taught it like that a few times, and I kind of memorised the equations and then used them, and the dummy variable always annoyed me and I couldn't quite grasp what was happening with it. So let's have a wee look at it in 3 dimensions, and I'm pretty sure when you see it in 3 dimensions you'll kind of have an aha moment, and it should be more apparent to you what's happening here. So here's our process of convolution shown in 3D. Now we had our original function, which was our f of t, which we've now introduced the dummy variable tau, we've called it f of tau. We also had our function h of t, again we've introduced this dummy variable tau, we've called it h of tau. We've then taken this function, which is our h of tau, we've flipped it on the y-axis, and it's become h of minus tau, and then we've slipped it along the tau axis here, and it's become h of minus tau plus t. So in effect that then becomes h of t minus tau. So we've got these two functions here, h of t minus tau and our f of tau, and we're going to slide this function over the top of this function here. We're going to form the product f of tau h of t minus tau, and then we'll integrate with respect to tau. Now I've drawn it out here in 3 dimensions, so we've split up the tau and the t-axis. Remember, they both represent time, but we've split them up and we've put them at 90 degrees. So this is our original axis t, so this is our time axis, and you see that the final output is going to be our convolved function g of t, which will be a function of time. But in order to get there, we introduce that dummy variable. So the dummy variable is shown in this direction here, so it sits at 90 degrees to this t-axis. So this is our dummy variable axis tau, and you can see that what we're going to do is we're going to slide this over the top of that one, and we'll form the product. So at that point there, I've drawn it at some, in effect, digital points, so just certain points along this t-axis, although it would exist all the way along it, but I've only just picked up certain points to make it easier to see. So we've waited for a certain period here of a time t, and at that time t we've moved this function over onto the top of this function, and we've multiplied the two together. We've got the area of which is the product of this function, and that's given by this little area here. So I'm representing this area here. Okay. Now we do that the same thing again. We leave it to move over the top a bit further, and we can see further along here we've got this little area here, and as this triangle moves into the entire surface or part of this this function here, we get the entire triangle, and we've drawn that here. And again, as this triangle moves outside this value of 1, then we're only going to be left with a little bit there of overlap. So we're just looking at the overlaps here as this signal here moves over that, and we've introduced a dummy variable in order to allow us to see them moving along each point in time. Okay, so then what we're going to do is after we form the product, we integrate in that direction. That is, we just take the area under this. So the area of this little section becomes the height of this, and again the area of this section becomes the height of this, and the area of this section here becomes the height here, and that area becomes that height. And we do that all the way along, and we do it in an analog fashion as opposed to this digital fashion which I've shown, and it generates the convolution of the two functions h of t and f of t, and this is a convolution here. Okay, so that helps to understand the idea of the introduction of the dummy variable tau into this, and I think it makes it a lot easier to understand the process of convolution. So we'll go now and we'll have a quick look at it, the idea of convolution in the frequency. So because we can convolve function not just in the time domain, we could convolve it in the frequency domain, and then we'll go ahead and we'll look at it in Matlab, and whenever you see it in Matlab again, it helps to cement your understanding. So we can also write an equivalent form of convolution in the frequency domain. So we can write our g of omega is equal to the integral from minus infinity to infinity of some function f of v h of omega minus v by dv. So it's the same setup as in the time domain, but these frequencies here, these components here are frequency components. Now we're going to look at the convolution in Matlab. Okay, so this is a printout of the simulation, but we'll get in just in a second. We'll actually look at the simulation live. So we're going to have our function h of t, which is now called h of tau. We've flipped it, and the y-axis became h of minus tau, and we're sliding it along this t-axis. So we get h of t minus tau, and this is our function f of tau. We convolve the two together, and you can see that where we have the overlap here, so for example at a point in time here we have this is the overlap. Okay, so that's the overlap, and the overlap will give you the height of the function here, which is your convolved function. So let's go ahead and we'll have a wee look at that in Matlab. So there's in Matlab, and what I've got here is our function f of t. Okay, just there, and our function there is actually a swap version of it. I think the function we used was in this direction, but it doesn't matter. We're taking this function here, h of t, and we're going to flip that function h of t over this axis, so when it comes in it'll actually come in like that. Okay, but you'll see that just in a second. So there you go, you can see the function coming along here. It's been flipped in that axis. Oh, can you see it now? Yeah, flipped in that axis, and it's continuing along here. Okay, and this is the convolve function in the bottom. Okay, and you see it's heading back out of this function here, so the area is dropping down and down and down and down and down and down and down till they cross over 0 again, and we can get into the very end. Okay, so that there is our convolution. Okay, so we've taken the square wave and the triangular wave. The triangular wave's been flipped in this on the axis, and then shifted along the time axis, and the area overlap area has been calculated, and the overlap areas are the height here. Okay, and this is the convolved function g of t. So convolution is a very important part of signals and systems. I hope that video's gone some way to describing it to you, and that's all there is for now, and I'll get you on the next video. Goodbye.